Hello everyone and welcome to the session 2 of day 2 of IndoML workshop. And this session there will be a lot of talks on ML applications beyond computer science, and the first speaker is Professor Udit Bhatia, who is an assistant professor of civil engineering discipline in IIT Gandhinagar, and he'll talk about robustness and recovery of built and natural systems subject to hydrometeorological extremes. So I'll say how to tackle these problems using complex network by integrating data and nonlinear dynamics. So Professor Bhatia is an assistant professor of civil engineering department at IIT Gandhinagar. His research interests include resilience of built natural systems, uncertainty assessment in hydroclimate extremes. And he got a number of awards, including Outstanding Graduate Research Award in Northeastern University at Boston's, Dean Fellowship in Northwestern University, then Director's Medal in NIT Hamirpur, as well as Best Graduating Student Award at NIT Hamirpur. So over to Professor Bhatia. Thanks.
A lot, Abir. Thanks a lot for this kind introduction, and hello everyone. So as the theme of this particular session suggests, that we would be talking about ML and broadly data applications beyond computer science. And I would also be talking about AI for data and data for AI, which happens to be the central theme for our IndoML, our Indian Symposium of Machine Learning this year. Now, in this talk, I will be talking about how community has been leveraging deep learning opportunities in the field of hydrology and hydrometeorology, how the end product that we get from our hydrological and hydrometeorological models feed into the resilience of built and natural infrastructure systems, which happen to be a multifaceted challenge, which requires cross-disciplinary and multidisciplinary solutions. And I will be briefly talking about three of our key research thrusts to demonstrate the philosophical understanding of the field and what specifically we have been doing in this particular field. Of course, a lot of groups have been working at this intersection of physics, domain AI, and physics, complex networks, and machine intelligence. But I will be specifically talking about examples from our work, which of course I'm eligible to do given the understanding that we have developed by working on these issues over past few years. And then of course I will talk about what are the ways going forward, where are the opportunities for computer science and domain scientists outside computer science to work together. So before I go into details and nitty-gritties of my model's results, I would first try to discuss that what our scientists and engineers typically expect from their models. We definitely expect that our model should be interpretable, and that's a long ongoing debate between machine learning community and domain scientists. And when I'm mentioning domain scientists, I'm typically referring to a group of scientists who are working primarily on physics-driven model, physical models, or physics-based models. We would expect our models to be physically consistent. We, of course, would want our models to be reasonably predictable without compromising the interpretability. But while doing that, we would also expect our models to preserve the complex relationships that exist between space and time. And to achieve these objectives, we have been playing with different architectures of very simple models that try to conserve basic principles of conservation of energy, conservation of mass, to all the way to complex models which account for teleconnections or long distance spatial connections within the domain of interest. And of course, we look into various metrics borrowed from machine learning statistics communities to understand how predictable our models are. And to achieve these objectives, we typically end up with two broad classifications of our models. One we safely say as physics-based models, where we try to emulate a physical system through certain set of equations. These equations, as I mentioned, they are either conservation of mass, conservation of energy, or they are empirical or semi-empirical in nature. That is, scientists set up their base at the point where they take a lot of observations, make a lot of observations, and based on the observations, we develop some semi-empirical relationships. And I will give some specific examples at how these relationships look like. And what we try to do is that using grid search algorithms, or now using uh, various machine learning approaches, we try to identify what is the best set of parameters that would help us establish the relationship between our inputs, what we often call as predictants, and what we want to predict, that is predictor. Now, the objective broadly aligns with what we also do in data-driven models. That is, we get an input and then we try to learn the output. For example, as a hydrologist or somebody working in hydrometeorology, I'm always interested in that if X amount of rainfall happens over given domain, how much of that would be available as a stream flow or flow in the river, because that is going to be a key characteristic controlling the flood dynamics at a given stretch for a given city or for a given region. And as we know that even in data driven model, we try to learn a lot of parameters. For example, here the classic example that I've borrowed is from a convolutional neural network, where we try to learn weights through backpropagation and other approaches. And in one of our specific researches that we did, we tried to relate the output, that is how much water would be available in the river, using various forcings, including surface temperature, soil moisture, precipitation, elevation, and so on. And then we typically say that this is purely data driven models, as we really do not care about the finesses of the physical processes or underlying equations, but our objective remains that for given set of inputs, how my output is going to be related to that set of inputs. Now, there was a very interesting article, or I would say a perspective in Science a couple of years back, where they were trying to draw the parallels that how a domain expert looks at the problem and how a machine learning expert looks at the problem. Now, for a domain expert, somebody working in hydrological, hydraulic modeling, we get the data. Then we want to establish the knowledge-based exploration of connectivity between various variables and explore the various hypotheses. That is, if we say that with every unit change in precipitation, there would be X% increase in stream flow. So these are typically driven by hypothesis, but the connection between variables, it's more constrained in a sense that we are very much mindful of physics driven relationships like conservation of energy and mass. The reason I'm using these two words, that is conservation of energy, mass, repeatedly, because that's what we all understand to some level. On the other hand, when we talk about machine learning side, we really do not care about the context driven approaches. I'm just talking about a purely data driven perspective taken by domain scientists. That is, we just want to automatically extract the features and then ultimately identify the labels, and then we can go with models with high complexity, of course being mindful of bias, variance, trade-offs, and so on. Similar thinking now percolated in our hydrological, hydrometeorological community, that yes, indeed, we want to establish the relationships between these stress, between the inputs and outputs, but using certain set of physical conditions. On the other hand, if we just take the physical perspective, or a physical domain, that this is how a typical hydrological model would look like, we can also achieve the same using a purely machine learning AI driven model, where we have certain set of inputs and then we go for output, and both of us within the four expectations, they meet certain objectives in some way or the other. However, if we look little bit more closely that what physics based models or physically driven models help us achieve, we notice that we are typically confined to a specific center of the possible function space that we can explore and that we might be exploring to establish the relationship between inputs and outputs. On the other hand, when we talk about the full function space, it really goes beyond the set of empirical, semi-empirical equations that we typically use in these models. So here I opened that what a physical based or physics based model looks under the hood in the context of hydrology. It's a very, very simple conceptual model. And you would see that all the processes from E1 to E11, they are connected through sequence of equations. Some of them take linear form, that is W is simply sum of S and P, whereas Y is a non-linear function of W, B, and A, and so on. And simultaneously, we solve these equations and arrive at the final target variable. That, but we and these equations have their grounding in physics. in a way that either they have been empirically or semi-empirically established, or they are simple conservation of mass in action. However, certain equations that they were developed outside the domain, for example, or developed for a plain region, apply to a hilly region and vice versa, may lose their generalizability as soon as these equations are applied out of the context. And that is where the machine learning space comes into picture. That is, we simply say that the target variable of interest, it's some nonlinear function of our inputs, a very, very simple machine learning model that we can train through a convolutional LSTM or LSTM, or by using simple machine learning approaches like support vector regression, even linear regression in some cases, which turns out to be very handy, specifically when we have to look into the sensitivity of each variables. Now, it appears simple that now we have models, we have data. Let's use best of the data where it is available. Now we are living in a petabyte world in hydrological community. So why not use machine learning where we can set up the relations between inputs and outputs using some nonlinear training with exhaustive computational resources that are available to us. But unfortunately, the AI revolution has not happened for us yet. So this is one snapshot that I always curious about, that how the technologies have emerged in last decade or so. If you look in 2017, deep learning was at pinnacle of expectations. And now when we look at the same hype cycle for emerging technologies in 2020, the word has been replaced by explainable AI. That is, we not only care about the relationships between input and output, but we also need to know that what is the effectiveness of these deep learning approaches in domain applications such as hydrology and hydrometeorology, which are immediately going to touch lives of uh, community, of the end users, and so on. So what's the need? So if I talk about how the volume of model satellite in situ data has grown in last 1 decade or so, we are already touching in 2020 more than 160 petabytes of climate / weather / in situ observations from various sources. And of course, since I am talking to a very well-learned computer science community, I need not put petabyte into context, but for somebody not from CS, it's a lot of zeros for us to handle. Now, but here is the opportunity as well as the need. So we have 4 V's typically falling into our radar now from hydrological, hydrometeorological perspective. We have huge volume of data, that is data in petabytes. We have serious velocity of data, the speed of change. For example, every 3 days, certain satellite products would also tell me that how mass movement of groundwater has taken beneath us, and that would give us sizable understanding of hydrological processes shaping of floods and droughts. We have variety of data. We have data from satellites, we have data from in situ sources, we have data from handheld devices now. So for example, LiDAR surveys that are conducted across the globe, we typically say them handheld when compared to the satellites which are orbiting in external atmosphere. So we have variety, and of course we have a lot of uncertainty associated with data, with these particular data sets. And what we expect is that once we get knowledge from this data, we want to extract small information, what we also call as big data, small data paradigm, that we get big data. But when we talk about extremes in hydrology and hydrometeorological events, they are the events which are of most interest to us. So we want information which is small and digestible. We want some real-time information. For example, Google AI has been powering the real-time flood forecasts across the nation, across multiple basins. So we want information which is real-time, which is critical, and which is actionable. And we, of course, want integration across the disciplines. For example, as an impact assessment engineer, I cannot just leave my work once I have the assessment of floods. I need to go beyond that and understand that what this flooding extent would mean for decision making, what it would mean for the impacted society, and what it would mean for relief, rescue, and recovery operations. And then, of course, with all these interventions, serious money is involved, serious manpower or human resources are involved. And hence we need some understanding of confidence and robustness. And this particular loop, that is the feedback between the four V's and patterns and knowledge, it keeps on going back and forth. Now, what are the opportunities? So few years back, people realized that in machine learning, now we have achieved serious accuracy with object classification and localization. So there was some hypothesis driven study that can we generalize the lessons learned from machine learning community for detection of patterns that give rise to extreme events, including atmospheric rivers or extreme precipitation events. There has been leaps of progress in super resolution and computer vision approaches where we can give a really coarse resolution image as an input and generate a finer resolution image. And ultimately, we started looking at problem of statistical downscaling and blending from the same lens. So tomorrow, one of my very good friends and speaker, Thomas Wendell, would be specifically talking about some of his work in the area of statistical downscaling and blending, where they actually started giving very coarse resolution inputs to convolutional neural nets and started learning that what would be the mapping between a coarse resolution and finer resolution images. We also learned a big deal in climate community and weather community when we talked about short-term forecasting, that from video prediction algorithms that is given previous time steps, how our next time step is going to look like. And of course, from natural language processing and language translation, some of the lessons that we learned from LSTMs, they generalize very well for dynamical time series modeling. And I would be presenting some of the specific examples. While these opportunities are, of course, there, but the five challenges still remain the same. That is interpretability, physical consistency, preservation of complex relations, limited labels, as well as all these approaches are computationally demanding. So one of the applications that again, the work that I was referring to is that you give a low sensor images and using super resolution algorithm, you are able to generate the high resolution, high quality image. So all the way from 1 degree to 1 degree, 1 degree is approximately 100-kilometer grid size. We were able to reconstruct the precipitation at the resolution of 1/8 in the resolution through some series of through a convolutional neural architecture, which accounts for the interpolated coarse resolution images at the target resolution, and of course certain uh, auxiliary variables such as elevation or terrain information or relief information and so on. Now we realize, so in our group, so this is the work that I jointly did with Mayank Singh, who is also present in the audience, where we started looking into the certain architectures, that how we can account for domain knowledge, how we can account for lags, how we can account for rightly chosen variables, and try to understand the progression in space as well as time. So, for example, we, after looking into the context, we realize that precipitation at certain place, in addition to the low resolution precipitation and elevation that previous studies were talking, it also depends on relative humidity, pressure, U wind, V wind, vertical velocity, and other meteorological variables that are governing the weather dynamics at a particular place. So yes, so addition of more variables has always been a topical interest for scientists and engineering domain. But what we also borrowed from LSTM or natural language processing community is that it's not only what happened on the same day with these state variables is going to influence what will happen at the final resolution. We need to be mindful about what is going to happen on the previous day, a day before, and up to a certain window. And that gave us a way to combine space and time. And we came up with this augmented convolutional LSTMs to generate finer resolution projections to understand that how various forcing scenarios, that is, emission scenarios, are going to control the precipitation in next 30 years, 70 years, and 100 years. Of course, I will not go in the details of the models here, which of course you can refer to the papers that I am being referring to. But what we realized is that when we were just looking at space or time, we were either missing teleconnections or we were missing the long memory processes, what we also call as Hurst phenomena in hydrological community. So blending this understanding of space and time using these convolutional LSTMs not only helped us beat state of the art, which is often compared against root of mean of square of errors or absolute bias or some efficiencies that are very specifically defined for the or widely used in hydrological community. It also helped us improve our overall projections of extreme precipitation, which is our uh, key variable of interest. However, I should hasten to add that while this was an accidental discovery, because our objective function was only mindful of means, but because of better representations of teleconnections both in space and time, we mechanistically uh, observed that the side effects, quote unquote, side effects are seen in terms of better projection of extreme precipitation events. But that being said, there is a greater need not only to just focus on space and time, but there is a clear need to relook into how we are training our algorithms, what is the objective function we are framing, and what are the theoretical guarantees for performance on extremes, which still remain key variable of interest for engineers and scientists. So once we were convinced that there is a power for machine learning in hydrological and hydrometeorological application, the another study that we started in our work was primarily motivated by this Burjan et al. Work that I mentioned that made its appearance in Science couple of years, where there was very well highlighted that there is a need to neither focus on the red dot nor just focus on the peripherals of the red dot, but there is a need to integrate physics and machine learning in a meaningful way. So we set up our experiments for a few Indian basins where we said that yes, we have good understanding of physics-based modeling, that how precipitation interacts with soil, for example, how soil interacts with groundwater, and how ultimately all these processes they add up in linear or non-linear way to give rise to stream flow. On the other hand, community has been using data-driven approaches, including LSTM, Lasso, Ridge, SVR, GPR, Bayesian LSTMs, you name it, we have it. Kind of a toolbox already exists in hydrological community where we give set of inputs and then try to establish relationship between inputs and outputs. But what was missing is that at certain processes, we have limited to no observations to validate the empirical or semi-empirical relationship that we have developed in the process. And that is where we would keep on using those age-old empirical, semi-empirical relationships out of context. We hypothesize that let us use best of the physics where we have full understanding of those equations. For example, conservation of energy and conservation of mass, they are not empirical in nature or semi-empirical in nature, but they should be abided by all physics-based models. On the other hand, I would have very less to little understanding about dynamics between recharge, groundwater storage, and groundwater discharge because I have limited observations. And even if I have observations, I would not be having extensive field studies set up to establish the empirical relationships that were developed a few years or few decades or even few centuries ago, which I'm still using blindly. So we realized that let us combine best of the physics and best of the machine learning so that we are not just focusing on the target variables, but we are also improving the predictions or predictability of intermediate variables, which, by the way, is one of the key limitations that we have always ignored in purely physics-driven architectures, that we will just focus on our target variable. We will make sure that inputs represent a physical space, and then we will try to map that relation using set of empirical and semi-empirical equations. And then we compared our results across the board. That is, we looked at purely physics-driven model, we looked at purely machine learning-driven models, and then the architecture that we proposed, which is physics-guided AI. So we realized that while both physics-based models and machine learning, purely data-driven / machine learning models, they help us achieve a very good performance or satisfactory performance in terms of capturing the end-to-end relationships. The intermediate variables, for example, between precipitation and stream flow, a lot of moisture losses happen in the process. These nuances are often lost. However, and secondly, it would be very difficult for us to capture the role of parametric uncertainty in physics-driven models because of the constraints that we have on our model structure themselves. Then finally, what we did is that as I mentioned before, that we replaced certain boxes of our physics-driven model using the proxies of surrogate models and try to come up with the better process representation, in a sense that wherever we have less confidence on our physics piece, let us replace it with a typical data AI toolbox. And then based on the outputs that we get at from our first piece, finally is fed into another box. And we notice that across the approaches, that is, if we compare the performance with out of the box machine learning and physics based approaches, the performance as well as uncertainty quantification was much better for target variable, which happens to be Q, as well as ET, in capturing seasonality, in capturing, of course, we detrended the data, but of course, in capturing the peaks as well as the means. However, this is just a starting piece on very simple hydrological model, but an integrated vision as we go forward calls for that how we can really integrate the petabytes of data into state-of-the-art hyper-resolution models that are making their space in hydrological community. Because we can keep on experimenting on these small parts and then realize that yes, there is a benefit. But unless we really demonstrate to the community the scalability, the adaptability to large scale models, these exercises would typically remain in back of the backyard kind of work. So there is a need going forward that how we would integrate the big data with so-called big models in that exist in the community to understand the that how the entire process is shaping up, while being mindful that best of the processes are represented, that is climate scale processes are represented through conservation of mass, energy, and momentum. Whereas weather scale processes or subsurface processes where we have limited to no observations, that's where we make use of machine learning / AI models to gain control. Finally, once we improve the predictions or projections of our hydrological / hydrometeorological extremes, our work is only half done. Because as an engineer, I don't only want to understand the magnitude of the problem, but I would also want to design that what is the intervention or strategy I should have to minimize or mitigate the problem, or once the problem happens, how I should adapt to that. And that is where the community has been moving from risk to resilience, or resilience has been becoming central part of all the discussions concerning risk and translational engineering. So, but the problem that happens with resilience is that it's a very uh, uh, it's a subject at its initial stages. There has been a lot of debates and discussions that what is the definition of resilience. Then somebody in Nature published a correspondence saying that there are more than 70 ways to show resilience, and each definition of resilience would take away from the another. On the other hand, when we look into impacts and likelihoods, the kind of events that are expected to have higher impact and higher likelihood in future, they are directly or indirectly related to hydrological or hydrometeorological extremes in one way or another. For example, extreme weather events, the rate on the top, that is the likelihood is also high, as well as when they happen, impact is also going to be high. And this is just like Gartner Hype Cycle, World Economic Forum publishes this very nice impact likelihood figure in their annual editions of annual reports. And you would see that extreme weather events have been occupying this top place for last few years. However, with advent in data sciences, with advent in our understanding our data gathering capacities, there is call from the community that we need to change the resilience paradigm. We need to learn from data. We just need to move beyond physical barriers and make data as the central piece of our decision making. And that motivated us, in addition to a few anecdotes that I'm going to talk about, that why there is a need to integrate data, dynamics, and complexity to solve these problems of today. So this is one example that I typically discuss to motivate that what it means for us, that when we talk about infrastructures, how data is coming into picture. So in 2012, there was a sequence of events that left half of India without power. There were delayed monsoons, there were heat waves, there was surge in agricultural water demand because that was July 2012 when Kharif season is at peak, and that resulted in increased stress on power grid somewhere between Bina and Jhansi in Madhya Pradesh and Uttar Pradesh border. By the evening of 30th of July of 2012, we were in the middle of world's largest power failure in terms of number of people impacted. So what, and not only that, the events did not stop at power going out. Industries were brought to halt, and of course, the railways network, which happens to be lifeline of our nation, was brought to halt in middle of the daylight. And people were just left wondering what happened. Of course, we blame aging infrastructure and overcrowded railways that we are beyond our capacities. But if you look carefully, the roots of these events were again in the natural hazard, which manifested it all the way from delayed monsoons to a failed power distribution system. Similarly, what we observed in Kerala, fast forward 6 years, that was a national scale event. In 2018, there were a series of floods. Yes, there was an extreme precipitation event, but that extreme precipitation did not stop at flooding. It resulted in triggering of landslides at multiple places. There were sequences of flooding for an extended period of time. Combination of landslides and flooding further resulted in debris flow. And for 2 month period, we noted there was a huge disruption to infrastructure. And that is what made us that was a time when I was defining my thesis, doing my PhD, and that made me really intrigued that how complex of a web we are currently into. And then we finally zeroed down that there is a need to look into these systems of systems using a unified tool. And of course, network became our first choice. So what we hypothesize is that even when we look at the hazards, they are not isolated, they are concurrent, they are correlated, as well as they are teleconnected. When they interact with our infrastructures of today, that is network multiplex of built systems or social networks, the impact is again on the network. And the societies that get fragmented, they are also well represented by societal networks. And similar lessons also generalized 6 years down the lane when we started or reconstructing the events of Kerala floods, that it was not just extreme weather or extreme precipitation event happening. It was followed by shallow landslides, debris flow, floods, which resulted in road infrastructure disruption due to cascading failures throughout the basin, cutting the communities. Not only build systems, we also realize that this network lens also generalized to ecological systems, which again have connections between the species, biomass exchange happening between nodes through the various relationships, which could be mutualistic, what we also call as symbiotic relationships, or simply prey-predator relationships. And we, as somebody working as a taking first step in the field of network/data, I started reconstructing the events of tsunami of 2003, power blackout of 2012, and simulated cyber physical attacks, all represented through networks on Indian railways, and some set of events on US airways, which of course both manuscripts can be accessed on our profile. But that made us intrigued that while network scientists have studied the robustness part very well. In fact, there was an article a few years back where the title was Destruction Perfected, and it was talking about how we should attack a network in an optimal way that the damage is maximum. But we realized that as an engineer, beyond damage, we are also interested in recovery. And then we started developing certain network science based, using both intuitive and non-intuitive metrics, that how systems should be prepared to bounce back once they are disrupted. And that's where network science helped us understand the sequence of events. Recently, another work that I've been doing with my collaborator Mayank Singh, we realized that it's not only single point perturbations that impact the network or bother the network. So we again re-looked into the data of various transportation systems that are available to us, and started looking into the dynamics of multiple attacks on a system, that how a network loses its functionality, and is there any way to identify that what would be the typical warning regions and tipping regions before we lose significant chunk of functionality when a system is subjected to multiple attacks or concurrent attacks. And of course, we looked into a synthetic system, that is Indian Railways network, US network, where we do not have much evidence of concurrent attacks, but we do have examples of concurrent failures. But here, the exercises that we were doing, they were more synthetic in nature. But this gave us idea that it's that in even in real world these kind of attacks have unfolded. And then we started re-looking into the Kerala floods, about which I mentioned in the prologue, that is what it would cost to rebuild Kerala after these kind of disruptions happen. So recently Google started this mission, what we call as expanding our ML based flood forecasting, where they are generating lot of flood maps using machine learning algorithms. And this particular tool has received significant attention. So we realized that this indeed is AI that is being used for data, because what is the output for these this Google platform is input for our integrated data and dynamical model, where we take best of the machine learning, best of the machine learning based flood maps that are available to us, integrate with our dynamical physics based models to understand how precipitation will manifest into floods, how floods will manifest into landslides and debris flow, and ultimately how these three events, that is model flood extent, satellite driven flood extent used for validation, and shallow landslides and debris flow, interact with our road networks and help us quantify the overall functionality losses in the system. This particular work recently got published, and it has been receiving some attention from policymakers within India, where they really want to understand what it would mean for our most critical road segments in the border areas adjoining Uttarakhand and Nepal. And finally, we realize that when we are trying to understand these data dynamics, how natural systems from where all these nonlinear dynamics understanding has been propelled would be untouched. So we started looking into these ecological networks, which are typically studied using uh, models of different dimensions and complexities, but at the end they are simultaneous nonlinear differential equations, and people try to understand what would be their tipping points and what would be the universal patterns of recovery. But what we realize that again, while a lot of focus has gone to understand tipping points, that how these systems will fall down, there has been limited to no efforts to develop quantitative frameworks to give us pathways of recovery, that which species are critical, what is the sensitivity of species introduction through various restorative or preservative mechanism. That's one of the recent work that my lab has been doing, to understand that how these network science and data science approaches can be leveraged to identify the sensitivity of reintroduction of species in the end, and we use models of different complexities to reconstruct the perturbed ecosystems across the board. So currently we have been looking into 30 ecosystems across the globe, and we have been finding quite interesting and generalizable insights, and this is the work that is in review. Finally, I would end my talk that why there is a need to go beyond risk and resilience, because there exists a lot of opportunities. There is a need first beyond opportunities, I would say, and there is a need to translate some of the work that is typically confined to lab to the language that policymakers can understand. So, for example, again, this is a snippet of the work that I did during my PhD, where we got a US patent for our work on recovery. That is how a small intervention that is changing recovery sequence powered by complex networks and data sciences can help us gain significant financial and recovery gains at the time when systems need it the most. For example, small tweaking in our recovery algorithms showed us that we could have saved additional $56 million in 3 days span when New York MTA was recovering from Hurricane Sandy. And that is why there is a need to go from vicious circle of policy myopia, outdated engineering practices, financial disincentives to improve guidelines, informed decisions, and planned interventions for a better and resilient work. So this is all from my side. Please feel free to write to me if you have any questions. And Abir, over to you. Thank you.
Yes, any question from the audience? Any question from the audience? I think there is one question. So the question is, when we say AI or ML or deep learning, problem is good dataset is rare. So what is data? Can you hear me?
Yes, I can hear you. I could not understand the question. Can you please
So
repeat?
the point is that the question has been from Mr. Ajay. So he asked that when you say AI or ML or deep learning, the key problem is good data sets are rare. So to make data-driven decisions, where can we find good data?
Oh, I see. I think that's a very valid question. As I mentioned that when we talk about uh, quality data is always a problem. And in fact, hydrologists, hydrometeorologists, they spend their significant amount of time to look into the consensus and accuracy, because we get so much data from different sources of the same variable, and you would notice great variations amid this. So yes, that is definitely an issue. However, that being said, I would say that that lot of data that is already available to us is also underutilized. So, for example, when we talk about, I was talking about these petabytes of data, the data that all these CMIP6 portals or reanalysis data portals give us. The the basic sanity check is in place there. You can also see that that all the output obtained from these analysis reanalysis models, they have some level of sanity check. But and that is where we are trying to first trying to understand or how to leverage machine learning the day when we have high quality data available at our disposal. That being said, I still say that the data is still underutilized in the way we are drawing our inferences using purely physics driven model or purely machine learning model, at least in the community or in the water community. What are
So
the
the next
ML?
question.
Yeah.
Yeah. I think you have gone to the question. Just for the sake of everyone, I just to point out. So what are the ML questions related to network resilience and tipping point analysis? This is by, I think, Professor Adya Mitra from IIT Kharagpur.
Yeah, Advay, I think again this is an excellent question. So specifically in the context of my talk, so so the second part, that is on network resilience and tipping point, it's primarily data driven. Uh, Community, of course, has been working on a lot of ML questions that is specifically looking into the role of reinforcement learning, for example, that how to understand the best incentive structures or incentive goals that can propel the recovery of systems, and specifically wherever resource allocation is involved, that's where reinforcement learning has been widely used to understand and model network resilience. But the key topic, the key challenge that still remains unaddressed there is the issue of complexity. So of course we want to deal with the spatial complexity in its most organic form, but immediately uh, the model complexity becomes very hard to get validated, and that remains one open question even in the area of resource allocation in the water community, to understand resilience of flow within systems and how we should prioritize recovery while being mindful of incentive structure. Also, is the hydrological community interested in using MLDLS surrogates? Of course, a lot of effort is ongoing, and if you do a quick scholar search, you would find a lot of papers dealing with surrogate modeling, and hydrological community has been trying a lot to address that gap. That being said, one thing that we have to realize is that most of these works are still at experimental stage, because that also goes back to the first question, that do we really have that high quality data to understand that what is the marginal gains of using these surrogate models instead of completely physics or AI driven models.
So there is another question by Mr. Dibakar. I think I had the same question. So basically this data or the traces has been generated by some underlying latent differential equation, right? Under the hood. So there has been some work in ML. In fact, the last 1 year, I think there was the best paper award in NeurIPS was on neural differential equations. So is there any scope to did you try to use this model, or there is any scope to use that kind of approaches where you can actually try to infer the underlying differential equation from data?
Yeah, certainly. I think specifically in the climate community, there has been a lot of interest to look into those kind of models and look into the underlying generational process and try to mimic the dynamical equations governing the system. My group specifically has not been looking into that, but I'm definitely aware of my collaborators who are working in this particular area. In fact, Thomas Wendell, who is going to talk tomorrow, that was one significant part of his PhD thesis also, where he was looking into similar kind of models. That is, can we also regenerate the underlying dynamical process slash equations for better predictability of these systems?
Okay, so any other questions from the audience? Okay, so I would like to thank Udit once again for the timely talk, and anybody who wants to catch up, he can catch up with. Okay, thanks.